So when you're dealing with polynomials, there's several different types of zeros you have. So I want to go and do a quick review of that first. So let's say you have y is equal to x squared minus 5. So that's a graph of a parabola, and you've dropped down 5, and it's still going to be going up. But the question is what are these zeros? To find those zeros, you go ahead and you would say x squared minus 5 is equal to 0, x squared is equal to 5, so x would equal to plus or minus the square root of 5. So these are irrational zeros of that function. One of the zeros is considered negative. This other zero here is positive. And that positive or negative is just based upon whether or not it's on the left side or the right side of the equation. Now, even though these are irrational zeros, they are still real numbers. And they are still real zeros. And that's because they cross the x-axis. Now, if I had another equation where it was y was equal to x squared plus 4, here, when I draw my graph is going up 4 this time, and therefore the graph never crosses the x-axis. Now, that does not mean it doesn't have any solutions. I can still solve this. So if I have x squared plus 4 is equal to 0, I get x squared is equal to negative 4. And when I take the square root of both of those, I just get imaginary solutions. And I get the fact that x is equal to plus or minus 2i. And this is a complex zero. So what we're going to be doing next is to talk about how to identify how many positive real zeros, negative real zeros, and complex numbers any polynomial function has. And that is called Descartes' rule of sign. So to determine the number of roots of any given polynomial, p of x is equal to ax to the n, all the way down to the coefficient. First thing is the degree. Once you know the degree of the polynomial, you know that the polynomial has n number of roots. Now, these roots can be imaginary, they can be irrational. So just to take a step back, any quadratic equation, in this case, will have two roots. It could have two real or two complex solutions. Now remember again, what we're talking about is a quadratic equation. I could have that parabola moving up. This would be an example of two complex solutions. It could be opening down with two real solutions. And if it touches the x-axis, and again, the roots or the solutions are the same thing. If there's only one, that is considered a double root, or that multiplicity that we've talked about. So what we want to talk about today, so we're going to want to find out if we have positive real roots, negative real roots, and how many complex number solutions that we could have. So the way we want to do this is with a chart. Now, first thing we're going to do is we're going to talk about the changes from positive to negative. So the number of real positive zeros in f of x is either equal to the number of variations in sign changes or is less than that by an even number. And the even number comes into play because of the fact that in order to be a complex solution, complex solutions always appear in pairs of two. So let's count the sign changes. Going from, this is a positive x to the third, that has one change. It goes from positive to negative. Negative to negative does not count as a sign change. And then negative to positive counts as, again, another sign change. So that has two positive sign changes. Now, let's go back to the degree for a moment. The degree of our polynomial is 3. So that means it has 3 real zeros. So that means it's going to have 1 negative or 0 complex. Now, let's go back over to the rule. Or the sign change is less than that by an even number. So if I go down from positive, I subtract 2 from that. That gives me a possible of 0 positive, 1 still negative, but that 2 that I subtracted from here now will change the fact that that could have a possibility of 2 complex solutions. All right, so let's first go ahead and count the variations in sign. X is positive, going to negative counts as 1. Negative to positive counts as 1 again. Going from positive to negative counts as 1. So the variation of signs here is 3. So the number of possible positive real zeros is going to go ahead and be 3. The max number of negative real zeros, we're going to go ahead and start that number at 0. And that's because the degree of this polynomial n is equal to 3. The maximum number of complex zeros is also going to go ahead and be 0 for right now. Now, this doesn't mean that that's the only possibility. The next possibility would be that if the number of real zeros gets reduced by 2. And if I drop that down by 2, then it could be 1 possible real zero. This stays in 0, and then the maximum number of complex solutions becomes 2. Now, how did I know that the maximum number of negative solutions stayed as 0? There is this additional rule that says this. If I go ahead and plug in negative x to my original function, which means that would be negative x to the third minus 12 times negative x squared plus 40 times negative x minus 24. And I see what happens there. And you get a negative x to the third. This x squared on the inside, when it squares, becomes positive, and it stays a negative 12x. Then a negative 40x and a negative 24. And this is the rule here. So as you can see with what I'm doing here, I plugged in negative x, and there are 0 sign changes. That also matches up with the fact that I had the 0 in the beginning and 0 here. You can always use the fact that whatever your positive number of real zeros are, that the number that is missing here can be determined by subtracting n minus your number of positive real zeros. However, this is your rule for double checking to make sure that you are correct. And as you can see, there are no sign changes. So this is how you use Descartes' rule of signs. I'll do one more example with you. So let's go ahead and count the number of sign changes. And that will give us 1 here, no change, 1 here, and 1 here. So that the number of possible, positive, real zeros, in this case, would be 3. Now, that means that the number of negative zeros, based upon the fact that my degree of my coefficient is 4, so to verify that, all I'm doing here for the negative one is wherever I have f of x, I replace it with a negative x. So you'll see that anywhere that you have an even exponent, that sign will stay the same. And anywhere you have an odd exponent, that sign will change. And you would be left with a positive 6x to the 4th minus 11x to the 3rd. That negative changes that to a positive, minus 51x squared minus 99x minus 27. So you'll see for this whole thing, there is only this one sign change. But again, you can always count on that formula working. All right, now what are we left with complex? So for the complex for this first one, it would be 0. It's always going to be 0 for the first time. Then take and subtract 2 from this, and you would be left with 1, 1, and 2. And that is how you would determine the number of possible positive or negative real roots and the number of complex roots of a polynomial.